Okay, so let us looking at this different performance parameter, and we are talking about overall efficiency, thermal efficiency, propulsion efficiency, and we have looked at how they vary. And another important factor that we have looked at is the takeoff thrust, because takeoff thrust is one of the important design parameter for any aircraft engine. As I already mentioned, this is the maximum thrust that one engine can produce, and this requires to be produced at the engine when it is on the static conditions, or rather it just on the run at the ground level while it is going to take off with the full payload, including the fuel load, complete fuel load and everything. So, that is the maximum thrust that one engine can produce, and how that can be varied, that we have already seen. Now, we are moving ahead with the other factors like range and endurance and all this. So, what we will discuss the range of aircraft. Okay. So, that is we are going to look at it. So, the range, when we talk about range, it means it says how far an aircraft can travel with a given supply of fuel, given supply of fuel. So, this is also an important performance parameter. And the range, actually the range depends on L by D ratio, which is lift to drag ratio, and thrust generated by the engine. Now, if we ignore, let us say if we ignore the climb to and descent from the cruise altitude, that means we are ignoring the climb and descent from the cruise altitude, and we can only consider the consider the aircraft to be at level flight. So, when we talk about the level flight, the engine thrust and the vehicle drag must be equal, and the lift on the aircraft should be equal to its weight. That means, if we look at the free body, let us say this is the aircraft, then this is thrust, this is drag, this is weight, and this is lift. So, they should be equal. So, T would be D, which is L into D by L, which is mg by L by D, because we have L is W is mg. Now, here m is the instantaneous mass, g is the acceleration due to gravity, d is drag force, which is L by D, or rather lift to drag ratio. Then we have thrust power, that would be Tu mgu by L by d, and what we have seen that overall efficiency is Tu m dot f q r. So, if we equate this term, what we can write, m dot f q r eta naught mgu by L by d. So, that gives us m dot f equals to mgu by overall q r L by d. Now, m dot f is also part of overall aircraft mass, and this is what m dot f is also getting consumed. So, dm by dt, since fuel is consumed, then what we can write, that dm by ds by dt, which is minus u dm by ds. So, where is one can assume that this is the distance along the flight path. So, now we put this back in this m dot f expression. So, what we get, u dm by ds mgu qr L by d. Now, if we integrate from m1, that is initial mass, to m2, which is final mass, dm by m equals to 0 to s eta naught L by d ds. So, this becomes ln m2 by m1 minus ds eta naught L by d, and that gives gs eta naught q r L by d. So, we get S is eta naught q r by g L by d ln m1 by m2. So, this is known as brackets range formula. So, what we see here, that S is proportional to eta naught. That means, if eta naught is higher, so we have higher range. Now, if we consider f is small and pressure term is neglected, then what we can write eta naught equals to by m dot f q r, which is u e minus by f q r. So, now we take derivative to the eta naught with respect to u for a given u e. So, what we can write, this is 1 by f q, u e minus 2 e is 0, that gives u is u e by 2. So, we have already seen that eta naught is max when u equals to u e by 2, and that is the same time also range is max, because range is also proportional to the eta naught. Now, let us consider a turbofan engine, which is essentially with double propellant stream. So, here we need to replace, because turbofan has one cold stream and hot stream. So, need to replace u e by the thrust averaged quantity like u e bar. So, where u e bar is defined as m dot a h plus m dot a c, m dot a h plus m dot a c, and fuel air ratio this is m dot f by m dot a c. So, this can be written as m dot f by m dot a h 1 plus m dot a c by m dot a h, f by 1 plus . So, using this average u e and this fuel air ratio, one write that eta naught would be 1 plus m dot a c by m dot a h u e minus bar by f q r and into u. Again, for a given u e, eta naught max would be u e bar by 2. So, we can take the simple derivative of that and find out that this would be u e by 2. So, eta naught also depends on flight Mach number. So, one can plot eta naught like let us say 1, 2, 3 like this. This is flight Mach number 0.2, 0.4, 0.6. So, eta naught this varies like this. So, eta naught increases as flight Mach number increases, and at the same time what we can look at is the L by D variation, how that goes with flight Mach number 1, 2, 3. This is flight Mach number 10, 20, 30. So, this is how L by D with the flight Mach number, and the other thing which Mach number, this is 5, this is very eta naught into L by D. So, the range should increase with Mach number, however, L by D also depends on Mach number. That means, range should increase with flight Mach number, however, L by D also depends on M. Now, L by D for supersonic is much less than subsonic, and L by D is maximum at high subsonic. For the product of eta naught L by D, this is also maximum at high subsonic. Okay. Now, for a given fuel consumption rate, maximum range is obtained at high subsonic flight. So, for a given fuel consumption rate, maximum range is obtained at high subsonic flight. Now, the other things like commercial aircraft, fly at high subsonic speed, for two reasons. One is economical, and second is that efficient operations. So, this is where the all our civilian commercial aircraft that fly most of the time is the high subsonic. So, typically they operate around Mach 0.7 to 0.8 in that range. So, this is high subsonic range. So, what happens that higher Mach number shock fronts in front of aircraft nose. Now, once that happens, if there is a shock formation, so we have already seen that across a shock the temperature increases. So, when the temperature would increase, obviously the thermal load will increase. So, thermal load on structure increases with m. So, to avoid this, the payload also so now these two thermal load or to be resistant, the structure need to be heavier. So, the structure need to be heavier to withstand all this. This is one of the immediate consequence that one can have as soon as this is. Now, obviously, having said that, it is quite obvious that supersonic flights are much less economical. For example, when Concorde can take 100 passenger and use more fuel than a Boeing 777, which can carry roughly around 500 passengers. So, they are not economical either. Again, looking back to that, so looking back to that range equation, what we get or obtain that L by D Q r by G ln m1 by m2, and eta naught is Tu by m dot q r. Okay. So, if we put this back, we can write S is L by D T by m dot U by G ln m1 by m2. So, which tells that T by m dot is an important parameter. Okay. So, T by m dot is an important parameter, and this is the specific thrust. Okay. So, that means the thrust generated per unit fuel mass of fuel consumed, mass of fuel consumed. Now, the other the reverse of it, which is m dot by T, this is called the thrust specific fuel consumption, that is TSFC. That means fuel consumed per unit thrust. So, just to produce 1 unit of thrust, how much fuel is consumed, that is called the TSFC, and this is one of the parameter which is often provided for providing an engine or configuration or something. I mean, if you look at or search in internet how these engine specs are provided, any engine manufacturer, they provides this kind of information, the TSFC, PRC, efficiencies, and then how much thrust it produces and such like that. Just to look at these things, this again these are generic term, just to extend these things for turbojet just to show you how things can be written for TSFC. T is m dot a F A u e minus u. Here, since neglecting pressure term, that is why we get this. So, our TSFC would be m dot F by T, which is m dot F by m dot A 1 plus F u e minus u. Hence, one can say that this is T by m dot A 1 plus F u e minus e. So, this is for a turbojet how one can estimate the TSFC value. So, similarly for turbo fan or turbo propeller, let us say for turbo fan or turboprop, you can just replace this u e by u e average. So, one thing is clear here that TSFC depends strongly on u e, that means what is the exit velocity. Now, let us say for any turbine engine producing shaft power. So, for turbine engine producing shaft power, what happens? So, we defined another quantity called the BSFC, which is m dot F by P s, that is called this BSF. This is fuel consumption per unit of shaft power to consider the thrust produced by hot gases also. So, this BSFC stand for brake specific fuel consumption. This is brake specific fuel consumption. Now, equivalent brake specific fuel consumption. So, this is we write BSFC is m dot by P E s, which is equivalent shaft power. So, that would be m dot F by P s plus T u. So, this is equivalent brake specific fuel consumption. Now, what we can see here that T is the thrust produced by the, so T is the thrust produced by the turbine engine exhaust. So, typically the engine brake specific fuel consumption would be some range like typical range of this would be 0.27 to 0.36 roughly kg per kilowatt hour. So, that is the typical value of BSFC which is there. So, you can see how TSFC and all these things they can be calculated, and also the BSFC and range. So, we will stop here and continue this discussion in the next lecture.